In this presentation, we'll take a look at SimpoMold, a standalone injection molding simulation software that helps you to predict and avoid injection molding manufacturing defects during the earlier stages of part and mold design. Using SimpoMold will avoid time-consuming and costly mold rework. We are looking at a smoke detector housing assembly. For this study, we will look more closely at the top cover to ensure its design and moldability. Since SimpoMold is not a CAD program, the first thing you may want to do is to analyze this model for proper draft. The injection molding process of plastic parts require draft in order for these parts to be ejected properly out of the mold cavity. Assigning proper draft to the part model can alter the part geometry and affect the part filling. Once you are satisfied with the draft analysis, you can continue with SimpoMold to optimize your plastic part design. After selecting the first part configuration, the next step in the simulation process is to mesh the model. We will use a surface mesh or shell mesh. We can specify the meshing parameters manually or decide to let the software mesh this cavity automatically. The triangle size can be set by entering a specific dimension or by using the slider. We can also manually adjust the mesh for small features like ribs, holes, and high curvature areas. We can also set the triangle size and allow the software to modify the mesh for these same features. You have complete control of the density and the quality of the mesh. Once the mesh is created, a project folder is created for the results, and it can be descriptively named to identify the specific results for a specific study. Now we need to proceed with the settings of the rest of the processing inputs and the boundary conditions. Notice the inputs in the Task Manager panel. The first input to select is the plastic material. SimpoMold includes a very extensive plastic material database with over 4,000 grades of commercial plastic. For this initial analysis, we will choose a grade of polycarbonate. Polycarbonate is a very good material with great impact resistance, strength, temperature resistance, and good insulation capabilities. It's an excellent candidate for this particular application. There are other parameters that can be set, but for this study, we will accept the default settings for the fill setting. The last step before running the analysis is to specify the gate location or injection location. Let's just pick an edge gate for a starting location. After meshing the model, selecting the material and the gate location, we're ready to run the analysis. After the pre-processing phase is completed, you can see that the preview results are dynamically displayed on the screen as the analysis is being solved. It's an extremely useful feature since it allows you to see when something has gone wrong in the early stages of the processing. You can then stop the analysis, fix the problem, and restart another analysis. If that change requires a change in geometry, you will need to remesh the part. The Analysis Manager also provides some valuable feedback. You can know what percentage of the model is filled, the processing time, and what the maximum pressure requirements are. If you find out that the maximum injection pressure is starting to peak or is simply higher than the maximum pressure of the injection molding machine, you would want to know at this point that this part is unlikely to be manufactured properly without a design change, a process parameter change, or maybe even a material change. As this analysis is running, the results are being generated. There will be a lot of different types of results that we're going to be able to look at. First, you will see the filling time plots displayed on the screen. Other plots like the injection molding pressure, average temperature, flow front temperature, or cooling time will also be available for your viewing. Analysis is complete will appear in the processing window when the analysis is complete and the results are ready for viewing. The first thing you may want to look at is the Results Advisor. Its access is located in the lower section of the Flow Results panel. This explains all the different kinds of plots and gives you some advice on how to troubleshoot and fix any potential problem. It also provides a short summary and displays a traffic light indicator that gives immediate feedback on the part moldability. To further gain insight, we can animate the fill time plot. Here we are looking at the flow of the melted plastic as it travels into the mold cavity. One of the major problems we have here is a phenomenon called Racetrack Effect. It's usually caused by a relatively thick wall section where the plastic in one area of the part races ahead of the flow front of the rest of the part. It may or may not be a problem for some situations, but in this case it has caused backfilling in the thin ribs that creates weld lines or net lines. Weld lines are areas where two or more flow fronts come together and form a weak bond which is easily broken. From a structural standpoint, this is going to be a very critical and definitely something to be avoided. We can also look at the air traps result. Air traps are places where air is trapped inside the mold cavity. If this location is a ventable location in the mold, there would be no problem. Air vents in non-ventable areas causes burn mark, a hole in the part, or in extreme cases, damage to the mold surface. The cooling time results plot indicates a substantial cooling time of more than 60 seconds due to the thick areas of this part. Now we will try a different configuration as we analyze multiple variations of this part so we can refine our design and find the best possible solution for our design. In an effort to fix the racetrack problem in this configuration, we decreased the wall thickness in certain places of this part, primarily around the perimeter. With the same injection location and material, you can see that we ended up with another problem because we decreased the wall thickness too much and created a short shot problem. No matter what you do, how you set up the molding machine, or how fast you inject the plastic into the mold, you will not get the plastic to fill the mold 100%. This molded part would be a defect that would make it unusable. Let's look at a new design iteration. This new configuration features a slightly increased wall thickness. Looking at the fill time plot, we see that this part configuration will fill the mold cavity 100%. Switching to the pressure plot, we see that the molding pressure required to fill the cavity is well under the maximum injection pressure of the molding machine at 100 megapascals. With the first iteration's heavy wall, the cooling time was long. This cooling time is the time necessary for the part to cool to the ejection temperature for this material. The ejection temperature is that temperature where it is safe to eject the part from the mold without deformation to the part. This configuration reduces the cooling time significantly by more than 50%. Wall thickness usually drives the cooling time, and the cooling time on average is often about 70% of the overall injection molding cycle time. This means that by improving the geometry of your model, you can reduce the cycle time, reduce the amount of plastics in the part, which will also lower the price of the part. Now the part is being filled correctly, but we still have problems with the weld lines located in the middle of the thin rib. This will require further refinement. A logical modification to improve the weld line location is to change the gate location to another area of the part. Let's open a new project showing those results. The great thing about SimpoMold is that you can run these multiple what-if scenarios to see what is going on and how to get the fewest number of weld lines and the best filling pattern. From the results, we see that the new injection location definitely helps to significantly reduce the weld lines, especially on the rib. However, you can see that with nearly 47 megapascals, our pressure to fill is still higher than preferred. If we were only considering a single cavity mold, our required pressure would work. In this case, we will be considering a multiple cavity mold and must consider the increase of the injection pressure requirement by adding a sprue and runner system. Another change will be required. So let's make a material change. We have a previously run analysis to show the effects of this change. We started with straight polycarbonate and now we're switching to polycarbonate ABS blend. It is a similar material to polycarbonate when comparing the material's properties and strength. Looking at our results, you can see that by changing to a new material, we still can fill the part well, and we managed to decrease the pressure required to fill the cavity by 20 to 25% to about 37 megapascals, which is going to help us manufacture this part more easily. Being satisfied with this design and having overcome most of our initial challenges, we should also look at the volumetric shrinkage. All plastic materials shrink. While you will see results for shrinkage at the end of fill, the volumetric shrinkage at the end of packing is more important. Changing packing pressure and time will actually affect what our volumetric shrinkage results are. Notice that this project was completed using both filling and packing analysis. Overall, we have reduced the volumetric shrinkage from the 10 to 12% range down to a 1 to 2% range after packing. Also, we have a much more uniform distribution with no significant changes from one end of the part to the other, so it's highly unlikely the part will warp or deform out of shape when it comes out of the mold. Now that we have optimized the part for manufacturability, and since the injection molding process is ideal for being a high-volume manufacturing process, we want to look at a multi-cavity family mold layout to mold the top and bottom of the smoke detector housing in one shot. This ensures that all the parts have the same mechanical properties, density, tensile strength, chemical resistance, and the same color and surface appearances. However, one of the problems is balancing the filling so that all the different cavities fill at the same time and under the same pressure. It's virtually impossible to figure out how to do that without the help of SimpoMold. Within SimpoMold, we can use the runner balancing analysis tool and specify the runner segments and the diameters that you want to vary. The multi-cavity runner analysis will figure out what size those runners must be to accomplish a balanced filling for all cavities. In this last configuration, you can see that the runner system is balanced and now has all 4 cavities fill at approximately the same time. In this quick presentation, you saw how we can use SimpoMold to optimize our design and come up with the best possible solution. SimpoMold is an invaluable tool for any mold or plastic part designer, packed with many useful features and tools, including report capabilities to easily communicate your results to any member of your organization or team. SimpoMold will help you to ensure that your mold will work the first time.